It's indeed quite long and complicated. Geometry, compatibility, and structure preservation in computational differential equations. I have to start by acknowledging Liz Mansfield, who helped me prepare this presentation, and she is also one of the organizers. Okay, the goal of my presentation today is just to give you a little bit of an idea of what are the principles that are behind this program and what we have been trying to do, and an overview of some of the activities, and I will also try to tell you just a little bit about the first breakthroughs that we have been having during the program. Okay, computational differential equations. Solving differential equations in a computer by computational methods. There are plenty of techniques to do that, and in our program what we are focusing on is structure preserving algorithms for differential equations. And there are in particular two big communities which have been working on these sort of ideas. One is finite element exterior calculus community. They are looking at spatial discretization and how to preserve topological structure of differential equation under numerical discretization. This is important because leads often automatically to converging methods, to methods that you are guaranteed are doing the right job. They are converging to the solution of the differential equation. The other area is geometric numerical integration, and this is a field of research where we're looking at differential equations which are time dependent. And so examples are, for example, discretization of Hamiltonian systems with symplectic methods. This is a topic that has been around for a long time, and most people in numerical analysis know what a symplectic method is. In between these two areas have not been so good at talking to each other during the years, even if the principles behind the two areas of research are kind of similar. So it has been our goal to bring them together and try to make them interact. In between the two areas, there is another sort of important field of research that is very strong here in the UK, which is PDEs in complex and evolving domains. And because the time dependence here is very important for the problems, because the domains are evolving, then this area of research in some sense is in between the two communities, and they are naturally part of being naturally part of our program. Okay, so first goal and first outcome. It's not just the goal, but we are very happy that we have been managing to do this. We've been able to merge two different communities and to make them talk to each other. You think this is a trivial thing to do? It is not. It is not. There has been several attempts to do this before, but we really believe that this time something is starting happening. Okay. Now everybody is aware of the popularity of machine learning and big data and things like that. It's a hype. It's a very important topic of research. Well, we are proud to say that we still believe in differential equations. And differential equations are everywhere. We have to prize this man here, and we are in the Isaac Newton Institute of Mathematical Sciences. Differential equations are behind the laws of nature, as Sir Isaac Newton has taught us. We believe that we cannot create good numerical solution of differential equations just looking at data. Data-driven simulations are not good enough. And we will still need, in the time that comes, to look at differential equations and their proper discretization, numerical discretization. Okay, so let me say something about the ideas. what do we care? What are the methods that we are looking at? We want sound, good, accredited method for ODEs and PDEs. We aim at encoding the laws of physics under numerical discretization. We want preservation of conservation laws when we discretize. If we know that there is preservation of energy, there is a symplectic structure, we want to try at least to preserve that under numerical discretization. We're looking at, for example, PDEs on manifolds, Lie group multibody systems, symplecticity, preservation of energy and momentum, preservation of potential vorticity in PDEs for climate, for example. Moving domain and moving mesh methods are also something that we are looking into. So we want solutions that are qualitatively good, sound, that respect the qualitative properties, but at the same time, we are interested in rigorous numerical analysis, not just good pictures, but also convergence analysis and error analysis when this is possible. And this brings me to a talk that was given here by Wayne Arter from the Column Plasma Physics Center. And they are doing simulation of tokamaks. They want to do plasma fusion. But these are big, huge investment, big machines they are constructing. If they cannot do proper simulations which are reliable and that we can believe in these simulations properly, they will be in trouble. They will make investments that are just throwing the money potentially in the garbage, right? So what else? Of course, we have to care about the efficiency of these methods. We have to care how fast the computations can be done. And sometimes to preserve structure is not always that easy, and it can lead to higher cost. So this is an important thing to study, how to exploit the structure and in the end of the chain have a method that is fast and computationally efficient. Okay, we have been considering different target areas, target applications during the program, in particular 4 of them, and we have had focused study periods. One, as I mentioned already, is plasma physics. And we have been looking at quantum dynamics. We had a study period of a couple of weeks with talks in that area. We had a workshop on computational general relativity at the beginning of October. And believe it or not, even if we still believe in differential equations, we are also interested in deep learning and neural networks and sampling. We had a focused study period on sampling algorithms on manifold last week. Okay, well, let me say something about the activities before I go over to some of the results. So we had weekly seminars, many of them, very many. And most of them are available online. Perhaps not everything, but many of them. We had a tutorial workshop at the beginning of the semester, which is also available online. So it should be really explaining some of the topics in an accessible way. We had a computational general relativity workshop with practitioners from general relativity. And we had, as I mentioned already, we had this future perspective workshop where we tried to discuss where the field is going, and we planned a collection of open problems as an outcome of that workshop. And as I mentioned, we had 4 different study periods. A Kirk lecture by Donatella Marini, which is also available online on virtual element method, and a workshop following that lecture. And then I want to advertise the Rothschild lecture, which will be given this Friday by Chus Sanserna, who is here in the first row. And we're looking forward to that event. So if you are around, it's highly recommended. Here is one of the publications that we have. We have a special issue, and at least 50% of the contributors to this book have been in the program and have been doing some of the work of the special issue during the program. So in some sense, this is the first publication coming out of the program. Okay, let me say just a little bit about two major breakthroughs that I just collected from people in the program yesterday. They are just two examples, okay? I'm sure that there are many more. I couldn't talk to everybody and get things explained from everybody. So the first one is from Caroline Lasser. I talked to her yesterday, and it's problem of vision, if I understand this correctly, is photochemistry. So in photochemistry, the big question is to understand and simulate with computational methods how do molecules transfer energy of light into motion. And this is important for the mechanism of our vision. So this is, as far as I understand, is a very computationally demanding task. So the computational chemists, what do? They do shortcuts. And they have some methods that are, so to say, heuristic. Now, Caroline has been thinking about these methods for a long time, for many years, and she couldn't understand why these things work. But now she tells me that she has understood the foundations, mathematical foundations of the methods, and she can explain them in a very nice way. So we are looking forward to these results when they will appear in journals, but she tells me that this is going to happen. Another result is about the multisymplectic discretization of Hamiltonian, multi-Hamiltonian PDEs. So multisymplectic structures are a generalization of symplectic structure that is well known in Hamiltonian systems for ODEs and is appearing always in classical mechanics. So what Ari Stern and Robert McLachlan have been studying and achieving lately is to design multisymplectic methods on arbitrary domains. And why is this an interesting thing? Because earlier this was was well known for finite difference methods, but finite differences are not so flexible when it comes to arbitrary shaped domains. And finite elements are much more so. So in this case, what they were able to prove was that in fact you can build multisymplectic method by using finite element discretizations of a certain type and combine them in a certain particular way with symplectic methods. So this is an important step forward in the field. Okay, so these were just two examples, and now we know that the program is just to bring people together, and we don't expect all the results to be found here. Also, we don't expect to be aware of all the results that have been. I've been reading a number of emails that were sent to Doug Arnold, who was trying to collect all the new results and the new activities that people have been looking into during the program, and it's a lot. We had 113 participants, and everybody sent something, so we have to look at it closely. But the results we are expecting are because we have been putting people together, is because we have a very, very good mixture of young people and experienced researchers in different fields. There are a number of unexpected results that are due just to the fact that people have been trying to collaborate and discuss with others that they didn't know they had something in common with. And also, finally, we want to acknowledge the help and support of the Newton Institute, who provided school and child care for some of our participants and disability provision for others, and who made the life of our participants so simple and nice so that they could do really their science. So this was really important. So watch this space, and the story is not finished. And thank you very much. I would like to, I hope you enjoyed the workshop. And if I have 2 minutes, I would like to show you a little video. So this is the message that I would like you to remember.
There are models, the differential equations that you need to solve. These occur in mathematical, biological models, climate, or classical mechanics. So you need to solve these equations, and you can't do that exactly. You need to do this on a computer using a numerical method. So you will make approximation errors, but there's no way around. Now the big idea about geometric integration is to pay close attention which errors you're making, and try to make these errors such that they don't screw up your picture, that you see qualitatively the correct pictures.
And what drew you to that area, Ruth?
Thank you very much.